And we're back. Okay, apologies for the delay. I'm Chris Merck. I work with Terry here in New York, building out the network here. I do some consulting on a number of projects, but the Things Network is what I am most excited about. Now today, I have a presentation prepared about propagation. So you should see the slides now. Can you all see the slides?
Yes. Yes.
Thank you. All right. So I'd originally wanted to talk about regulation and radio theory, but as I looked into the regulation, I discovered that every country has slightly different rules, and it wouldn't really be fair to give a talk to the global community about regulation in the United States. So I expanded the theory section a little bit, and want to specifically talk about propagation around 900 megahertz. Propagation is how the signal gets from the transmitter to the receiver, and lots of interesting things can happen in between, and what we do there can affect how effective the Things Network will be. So just some quick preliminaries. Number one, I want to show you where we are on the map, where we are in the spectrum. So the Things Network in Europe and United States is operating around 900 megahertz, a little bit lower in Europe, a little bit higher in the States. We are in the UHF part of the spectrum, ultra high frequency, above VHF where FM radio operates, and below super high frequency where satellite broadcast occurs, around 5 gigahertz. As you go lower in frequency or higher in frequency, the properties of the signal changes. So at very low frequencies, such as long wave radio down in just the hundreds of kilohertz, we see very high range, but you also need very large antennas because of the increased wavelength, and you have a very small amount of bandwidth available. This makes the spectrum at the lower end of the scale very valuable, and so there's a lot of regulation there. And it's not possible to set up a free-to-use network at 100 kilohertz because there's just not enough space for all users. As we go to higher and higher frequencies, up into the gigahertz, we have lots of spectrum available, but the range is seriously reduced. Right in the middle, there's this sweet spot here, as BBC refers to it in this image, where you have enough bandwidth that you can get many users and do useful things with the network, but the regulations are somewhat relaxed, and there's an opportunity for us to even set up that free network. So I just wanted to show that balance to kind of explain why we're in this 900 megahertz region. The second preliminary is about decibels. So for the less technical folks here, I just want to cover very briefly what a decibel is. So radio signals vary in strength over a very wide range. A practical example is a node that's right next to a gateway has one signal strength. A node that's 10 kilometers away that's just barely making it into the gateway may be 10 billion times weaker than the node that's immediately next to the gateway. And writing down all those zeros and doing calculations with numbers in the billions just becomes very inconvenient. So what we do is take the logarithm of the signal strength, or the logarithm of the ratios of the signal strengths, and we multiply it by 10 and then write dB after it. So instead of saying one node is 10 billion times stronger than the other, we say its signal is 100 decibels stronger than the other. The bottom line is all you really have to remember is 10 dB means 10 times and 3 dB means 2 times. To get into more details about this, even if you're not very technical, I really recommend this tutorial from Michael Osman, where he goes into decibels and does this beautiful graphical explanation. But for the time being, that's all you need. So let's talk about propagation. So if we have a transmitter here and a receiver some distance away, I've drawn towers, but these could be any transmitters and receivers on any frequency. What affects the ability of these two devices to communicate? Specifically to LoRaWAN, where does this 10 kilometer maximum range come from? And how can we optimize that range in a practical way? First, let's look at the transmitter side. So your typical transmitter, here's an RFM95 that I know many people are using. This puts out maximum about 20 dBms of power. That is 100 milliwatts. If you're not entirely sure what that means, just think of the power as being 20 decibels. As the transmitter sends its power out to the antenna, there's some kind of feed line in between that transmitter and the antenna. This may just be a trace on a printed circuit board, or it may be a piece of coaxial cable. Here I've written 2 decibels feed line loss, which might be typical for an embedded application. So by the time you get even just to the base of the antenna, we're already down to 18 dBm of power. Now, the antenna doesn't necessarily radiate all of the energy that hits it from the feed line. Due to mismatch between the antenna and the feed line, what's known as an impedance mismatch, some amount of that power is actually reflected back to the transmitter. Eventually, most of the power gets out, but you will experience some amount of loss no matter how well matched the system is. So here I figure 1 dB of antenna mismatch loss. Then the antenna has a certain radiation pattern. So whatever antenna you're using, you can look up the data sheet and see what that radiation pattern would be. The most salient number is the antenna gain. In this case, I've chosen 2 dBi, which is a gain of the antennas that come with many of the development kits that we use, a sleeve dipole. So this gain of 2 dB means that the antenna is focusing the energy that it's transmitting in one particular direction, in this case in directions perpendicular to the orientation of the antenna. It's focusing the energy there such that there's a peak that's 2 dB stronger than you would otherwise expect if the antenna was a point source. This is a trade-off because directly above and below this antenna there's going to be a null where there's less signal strength. Anyway, for the purposes of discussion here, let's just figure that the receiver is perfectly aligned with the transmitter antenna. So ultimately, out of the transmitter antenna, we're going to see effectively 19 dBm of power. That's known as the transmitter EIRP, or effective isotropic radiated power. So there's a formula down at the bottom. Just the important thing to note is that the positive terms here, like transmitter power, if you increase them, you increase the amount of power that comes out the antenna. If you increase the losses, like the feed line losses, by using less expensive cable or less well-matched instruments, you'll have less effective radiated power. Now, between the transmit antenna and the receive antenna, there's at least free space. There may be obstacles, but for right now, let's just figure that there's free space in between, and 10 kilometers of free space. There's an equation that you can use to calculate how much loss there will be over that link. In the case of 10 kilometers and 900 megahertz, it comes out to be 111 decibels. So our 19 dBm of power going out that transmit antenna, we only receive negative 92 decibels, negative 92 dBm of power at the receive antenna. This is less than 1 picowatt. That negative 92 dBm goes into the receive antenna. There's a receive antenna gain, mismatch, and feed line loss, just like we saw on the transmitter side. And ultimately, we receive, in this example, negative 93 dBm of power at the receiver. Even though that's less than a picowatt, it's enough power for that Semtech chip to demodulate the LoRa signal. We can receive down to about negative 120 dBm. So if we have perfect line of sight, you can go about 10 kilometers, and you still have a bit of signal margin here. We're at negative 93. We can go down to negative 120. The bad news is that there's obstacles. there may be 2 brick walls and reinforced concrete in between the transmitter and the receiver. In this example, you have 5 dB of attenuation from the brick wall. That means the brick wall absorbs more than twice the energy that comes into it. Less than 50% of the energy that goes into the brick wall actually comes out the other side. After going through several buildings, the signal may be attenuated so much that it cannot be received at the other side. And this table here seems not to be displaying correctly, but at this link you can, indoor path loss, which I'll share, you can see what the losses you can expect through brick, glass, masonry, reinforced concrete. So the good news is that at 900 megahertz there's lots of reflections. Nearby buildings can create alternate paths for the signal to follow, and although there's a loss at the reflections are often enough to get a signal through even in dense urban environments. Other good news is that the atmosphere actually refracts signals. The radio signals don't travel in perfectly straight lines. This is because the air is getting cooler and less dense as you go higher up in the atmosphere. So there's a rough formula here that based on antenna height, taking this refraction into account. If you have an antenna of height h meters off the ground, you can use this formula to calculate about how far that radio horizon would be, the farthest that you'd be able to reach, assuming that you have enough transmit power to get there. So for an antenna 1 meter off the ground, you can expect about a 4-kilometer radio horizon. But if you put the transmitter or the gateway up on a 10-meter pole, you're now looking at a 13-kilometer horizon. So we see the importance here of getting the gateway antennas up high. Another type of propagation that occurs in between our antennas is called knife edge diffraction. This happens a lot in urban environments. So a building or a mountain may block the transmitter and the receiver antennas, creating this shadow zone. However, as that signal passes over the knife edge at the top of the building, it creates this diffraction pattern, and it actually allows some signal to get into that shadow zone. The coverage will be spotty, but it's actually very important in urban propagation, and this is how a lot of our signals are actually being transmitted, especially in New York where we have so many tall buildings. Another type of propagation that does help us to a certain extent is called troposcatter. So in the lower 10 kilometers of the atmosphere, there's enough particles in the air that they actually scatter small amounts of the radio signal back down to Earth. At 900 megahertz, if you use enough power, you can actually reach up to 800 kilometers away. That's way beyond the typical radio horizon by pointing the antennas up into the air and scattering off the upper atmosphere. Now, 800 kilometers can only be done if you're using large linear amplifiers, which is only legal for use by the military and radio amateurs for non-commercial use. However, to a limited extent, this scattering is helping us day to day as we connect nodes to gateways. Finally, there's one other type of propagation that we see intermittently at 900 megahertz called ducting. So at night, this happens most often at night where the Earth is cooling off, and the Earth will cool off faster than the air in a layer just above the surface of the Earth. And this creates what's known as a temperature inversion, where there's a pocket of warm air just above the ground and then cooler air above it. This can trap signals and cause the signal to be ducted, almost like a fiber optic cable, and transmitted way farther than it ordinarily would. Experimenters very often communicate at frequencies at 900 megahertz and above, up to 24 gigahertz, I believe, between California and Hawaii, using temperature inversions that occur almost nightly there. So we're not going to expect to get that 2,000 mile or almost 4,000 kilometer range with the Things network at these low powers. However, I would not be surprised if we see occasional reception from nodes up to 200 kilometers away when conditions are right. So don't use a gateway's GPS coordinates as a a firm number. We may see connections much further, but they will be sporadic. So, taking that all into account, what can we actually do about it? What can we practically do to improve the performance of the Things network? So, first of all, we can minimize losses. So, when you're setting up a gateway, you want to minimize the feed line losses. That is, the coaxial cable losses between the gateway and your outdoor antenna. A good rule of thumb is to keep it under 1 decibel. This is an error. I should say less than 1 decibel. So if you're doing up to 10 meters of cable, you should use at least the LMR 400 type coax cable. If you Google coax cable losses or use the link at the end of the presentation, you can see what losses are for different types of cable if you need to go farther than 10 meters. Secondly, you should be careful to make sure that your antenna is matched to the frequency on which you're operating it. So in Europe, don't use an American antenna and vice versa. That might seem obvious, but there are some wideband antennas that actually aren't so well matched. So when you look at your antenna's data sheet, make sure that it has an SWR or VSWR of 1.3 to 1 or less. If you really want to be sure that your antenna is well matched, you can use a device called an antenna analyzer. They're a little bit expensive at 900 megahertz, but if you're installing many gateways, it may be a worthwhile investment. The antenna analyzer will actually tell you if the antenna is resonant at the frequency you're trying to use it at. You can keep losses down by using good connectors. So for 900 meg and above, we should really be using type N connectors wherever possible. They're a bit bulky, so they shouldn't be used on nodes, but on gateways, we should stick with type N connecting to the antennas. Let's see, on nodes, you should try to minimize your antenna mismatch on the node as well. There it's a lot more challenging to measure because it's small, it's difficult to get instruments in there, and many times people are using just small whip antennas that are manually cut to length. So the only advice I have there is just follow reference designs exactly. Read the manufacturer's recommendations on what type of antenna to use, what type of feed line to use, and just follow it to the T. There are ways to measure it if you have an antenna analyzer, but it gets a bit tricky. Height is the biggest way to minimize losses. Height, every time you raise your antenna up another meter, whether it's on the node or on the gateway, but particularly on the gateway side, it just really increases your range and decreases those path losses, gets more signal over the buildings, and just improves the situation all around. On the gain side, one thing you can do on the gateway is use high gain antennas. So instead of using the stock 2 dBi antenna that comes with, say, the Multitech conduit gateway, you can use a 6 or 8 or even higher dBi antenna that will give you some extra range. This focuses the energy in a horizontal plane, so it is a bit of a trade-off, but when you're trying to connect to a node 10 kilometers away, it's very much in that horizontal plane. So using high gain antennas is great. You just need to make sure they're installed vertically. Similarly for the nodes, if possible, you can use a sleeve dipole. Although for many applications, we'll need to use a chip antenna. Finally, we can discuss this, but higher transmit power means longer range. It also means you can use a lower spreading factor and consume less airtime. So your node should be capable of high transmit power even if you don't necessarily need it. Here's a quick image of some tests that we did in Brooklyn using Brooklyn's first gateway, courtesy of our member Manny. It was on the 3rd story roof with an 8 dBi antenna. And we walked around and measured the signal strength around about 6 blocks away, and we found we could get 900 meters through the blocks. And here there's just many buildings in the way. Many of these buildings are tall apartment buildings and office buildings. This is a really difficult environment, almost as hard as Manhattan. But we were able to get just about a kilometer away and still receive the signal. The only place we lost the signal was when we walked into this parking garage here, where there's reinforced concrete all around it, and we were on the basement floor. So that was actually very encouraging for us that we were able to get this much range in this difficult environment. Lastly, I'll just leave you with a couple references. You'll be able to click these when we post the slides. There's a coax loss chart that allows you to calculate feed line losses if you're doing outdoor antennas for your gateways. There's some SDR tutorials from Michael Osman. He's really a genius when it comes to explaining things in an easy and fun way. He also sells open source hardware gadgets for RF, like HackRF and Yardstick One. So if anyone's interested in diving more into how RF works and maybe experimenting with SDR, definitely check out Michael Osman. Lastly, a source for most of the material I presented about propagation can be found in the ARRL Handbook for Radio Communications. It is geared towards amateur radio operators, but it gives the best practical coverage of electronics, antennas, and propagation that I've really found anywhere. So that could be really helpful for our people installing gateways and building nodes to think about RF and make decisions that will result in that best possible link budget. And there, for the records, a table for different types of coax and their losses. The cable that I recommended was LMR 400, which you see has 12.8 decibels of loss at 900 megahertz after 100 meters. So you see at 10 meters, we've got 1.2 decibels of loss on LMR 400. You really don't want to go above that 1 or 2 decibel of loss on the feed line. So feel free to ask some questions on Twitter, and maybe we'll have some time to answer them at the end. Thanks for watching.